I'm going to talk about solids of revolution. I will assume that you're familiar with the basics of integration. If you're not, I would invite you to watch the necessary videos. All right? So let me now state what solids of revolution are. Solids of revolution are three-dimensional shapes created by rotating curves about lines. Solids of revolution are what you get when you rotate curves about lines. Here are some examples. Give me a moment to make a few pictures. Okay, so on the left side, I have two parallel line segments. I have a blue line segment and a black line segment. If I rotate that blue line segment about the black line, can you see that that will trace out a cylinder? Something that looks like that. So therefore, we can say that cylinders are solids of revolution. You see that? Now, for the blue and black line segment in the middle, okay, what shape would I trace out if I rotated that blue line segment about the black line segment? Can you see that that would trace out a cone? It would look something like this. All right. So therefore, cones are solids of revolution. And then the third example, the one farthest on the right, I have a half circle resting on a black line segment. If I rotate that half circle about the black line, can you see that that will give me a sphere? Okay, some soccer ball type shape. So therefore, spheres are solids of revolution. So there are many shapes that can be interpreted or defined as what you get when you rotate a curve about a line. Okay? Now let's talk about how one might calculate the volumes of solids of revolution. Give me a minute to make a picture. Suppose I wanted to find the volume of the solid of revolution created when I rotated the portion of the plot of f of x with respect to x values between a and b. I rotated that portion of the plot about the x-axis. Okay? So that might look something like the picture that I've drawn. Now, let's start by approximating that complicated shape with simpler shapes. So, cylinders are a simpler shape. What if I took several cylinders and put them next to each other? Now, I'm going to take various cylinders with different radii and maybe even different heights. Okay? And if I'm careful in the set of cylinders that I choose, then those cylinders might make an accurate approximation to the volume that I'm looking for. Okay? So those purple figures that I drew each correspond to a different cylinder. Okay? If I summed the volumes of all the cylinders in my set, that would be my approximation for the volume of the original shape that I was interested in. If I wanted to improve my approximation, I could simply use more cylinders that more accurately approximated the shape, right? Okay, now in the limit, as the thickness of or the heights of the cylinders went to 0 and the number of cylinders went to infinity, I would have the exact volume, okay? And we're going to be able to express that limit as an integral. And that's how we're going to use integrals to find the volumes of solids of revolution. So let's think about what the volumes of the cylinders, what expression they correspond to. So can you see that every cylinder corresponds to some interval of x values? All right, so for example, the third cylinder corresponds to some x value, let's call it c. And once we know that x value, we can find an approximation for the radius by calculating f of c. So the radius is approximately f of c. If x is a value that is in the interval that corresponds to that cylinder. All right. Now, you may know that the volume of a cylinder with radius r and height h is pi r squared h. Okay, so we've got the radius taken care of. What about the height? So can you see that the height of my cylinder is going to correspond to some delta x? Okay, it's going to be the difference of the biggest x value and the smallest x value with respect to the corresponding x interval. So, putting it all together, the area of that cylinder is pi times f of c squared times delta x. Okay? So, in the limit, as we add more and more cylinders, we will have the integral from a to b of pi times f of x squared with respect to x. Okay? That's our formula for the volume of this solid of revolution. Okay? So think about why the integral that I've written there gives you the volume of that solid of revolution. Now, let's do an example. Suppose I wanted to find the volume of the following cone. The cone that I get when I rotate a segment of a line about the x-axis. So the line that I'm going to rotate is the line that corresponds to the function 3x over 10. Okay? And I'm going to rotate the segment with respect to x values between 0 and 10. Now, before we use the formula to calculate the volume of a solid of revolution, let's use our knowledge of geometry to see what we would get without calculus. So the volume of a cone with radius r and height h is 1/3 pi r squared h if it's a right circular cone. And so the cone in the picture has a radius of 3 and a height of 10. The reason it has a radius of 3 is because the point with the biggest y value is 10, 3. You can see that by evaluating the function with respect to x equal to 10. All right, so then the volume of the cone has to be 30 pi. So now let's see what our integration formula gives us. So the integral from 0 to 10 of pi times the function squared, because the function expression corresponds to the radius, and then integral with respect to x. And we don't need the 1/3 because we're summing up cylinder volumes with respect to the integral. Okay, so let's see what that gives. So let me pull out the pi, and it's 3 squared over 10 squared, so 9 over 100 times the integral from 0 to 10 of x squared dx. So pi times 9 over 100 times what I get when I evaluate x cubed over 3 with respect to 10 and 0. So if I plug in 0, I'll get 0. And so that'll leave me with pi times 9 over 100 times 10 cubed over 3. And let's see what happens now. So 9 over 3, that simplifies to 3. 10 cubed over 100, that's 1,000 divided by 100, that simplifies to 10. And so the answer can be simplified to 30 pi, which is what I got before. Okay? So make sure you understand that example. Now, I'd like you to try to use our formula to find the volume of a solid of revolution. All right, suppose I rotated the segment of the plot of the square root of x with respect to x values between 0 and 6 about the x-axis. Can you calculate the volume of that solid of revolution? It'll have some kind of bell shape or almond or Hershey's kiss shape. So pause the video and see if you can calculate that now, if you like. All right, so I'll go ahead and calculate it as well. So when I rotate that segment of the graph, I'll get something that looks like that. And so the integral is going to be the integral from 0 to 6 of pi times the square root of x squared with respect to x. So that's pi times the integral from 0 to 6 of x dx. Pi times what I get when I evaluate x squared over 2 with respect to the limits. So that'll give pi times 6 squared over 2, and that's equal to 18 pi. Okay? Would you try this example now? I want you to calculate the volume of the solid of revolution that you would get if you rotated the portion of the graph of y equals x squared with respect to x values between 0 and 4 about the x-axis. Okay? So pause the video and do that now if you can. Okay, so I'll go ahead and work that out as well. So let me first draw a picture. By the way, pictures are almost mandatory when we get to some more complicated solids of revolution. So you're going to want to get in the habit of drawing pictures and not try to be a hero and do everything in your head. So the portion of the graph of x squared that I'm interested in looks something like what I just drew. And if I rotate that about the x-axis, I'll get something like this. Looks kind of like a sideways volcano. All right, so to calculate that volume, we will calculate the integral from 0 to 4 of pi times x squared squared with respect to x. And so that will give pi times the integral from 0 to 4 of x to the 4 dx, or pi times what we get when we evaluate x to the 5 over 5 with respect to the limits of integration. So that'll give pi times 4 to the 5th over 5. And let's see, so pi times, that's the same as 2 to the 10th over 5. I happen to know that 2 to the 10th is 1024. So 1024 pi over 5. All right? I hope that is what you got.